All right, class, welcome back. It's good to see you again. So last time we talked about empirical friction loss formulas. These are designed to make your life easier when solving for hydraulic design problems that depend on frictional losses. So we introduced three different models. The first is the Swamy-Jain approximation for computing the Darcy-Weisbach friction factor. So this is used with the Darcy-Weisbach model for head losses, but it's another method for finding that friction factor coefficient F instead of Colbert-White that doesn't involve an iterative solution. We also introduced the Chasey-Manning equation. So this is a similar model, mostly used for open channels, but we showed how it could also be used for pipe flow. And then we introduced the Hazen-Williams formulation, which is another empirical model used mostly for pipe network design in the United States, but it's one that you will commonly encounter. So today I'm going to move on to our last topic in single pipe flow. So after this point, we're going to be getting into pipe networks. Today's the last topic, which is kind of a review of some material from fluid mechanics with applications to hydraulic design problems. We're going to be looking at minor losses. So minor losses refer to energy losses in fluid flow resulting from changes in the geometry of flow or the direction of flow. So you encountered minor losses in fluid mechanics. What are some examples of things that can cause minor losses? Yes. A bend in the pipe, very good. So you may have minor losses associated with pipe bends. So in this case, you'll have some flow coming through the bend. And usually on the inner part of the bend, you'll get some kind of formation of turbulent eddies where the streamlines separate from the wall of the pipe and generate these turbulent eddies that cause energy losses. What's another example of a minor loss that you encountered in fluid mechanics? Yes. A change in diameter. So there's two primary types of changes in diameter. What's one example? It's a small diameter to a bigger one. So that would be an expansion. So we might have minor losses due to expansions. So a smaller pipe going into a bigger pipe. You'll get something that looks like this. These streamlines diverge as they go into the bigger pipe, and you'll get, again, some turbulent eddies that cause energy losses. On the other hand, you also have contractions, where a bigger pipe goes into a smaller pipe. In this case, you'll also get streamlines that converge. They go into this smaller pipe. You'll get some turbulent eddies forming both on the inside of the smaller pipe, as well as in this stagnation zone where the bigger pipe transitions into the smaller pipe. And there's one last type of minor loss that I'm going to talk about. It's not really conceptually different from the other ones, but it's one that we often will have to treat separately, and that is losses in valves and other control structures. So let's say we have a valve. It's going to look something like this, kind of like a piece of candy. And we'll have streamlines coming in. And even when the valve is completely open, it will cause some changes in the flow paths and our streamlines that cause these turbulent eddies, which result in losses, energy losses. So these are the main types of minor losses that we're going to be talking about. As the name implies, generally these losses are less significant than frictional losses. So frictional losses are sometimes referred to as major losses. Minor losses are usually less significant, but not always so. So there are particular cases in which minor losses can be significant, especially when you're dealing with shorter pipes or very disruptive control structures like certain types of valves. measurement devices can also cause minor losses that are significant. So they can be quite significant, and it's something we need to account for in analyzing and designing hydraulic systems. Are there any questions on the general types of minor losses before I move on? So in general, we're going to use one equation essentially for computing minor losses. All of the minor losses will take the form of the following general equation with some differences. So the general equation for minor losses is a quadratic function of the velocity of flow. So in general, our losses, our minor losses, h little l, will be of the form some coefficient k times u squared over 2g. And the coefficient is going to depend on what type of loss we're talking about. And the velocity that we pick also might depend on the type of loss that we're talking about. But generally, our expressions for the minor losses will take this form. So let's go through, and I'm just going to survey the major types of minor losses that we'll be talking about in this class. I'm going to start with contractions. So let's talk about sudden contractions. I'm just going to go through the list, basically, of all the different types of minor losses, talk about each one, and then towards the end of class today, we're going to go through an example that synthesizes both major and minor losses in a single problem. It's a good chance to review for the upcoming exam. So first, let's look at sudden contractions. This happens when a larger pipe transitions into a smaller pipe. So this is pretty common in water distribution networks, other types of plumbing. You might have a large water main transitioning into a service pipe, for instance. We'll get something that looks like this. And we can look at the streamlines. So as I mentioned before, you'll have streamlines that converge as they move from this larger pipe to the smaller pipe. And then two different things happen. So first, there's this stagnation zone that forms in these pockets where the larger pipe transitions into the smaller pipe. You'll get turbulent eddies that form within these stagnation zones that result in energy losses. So in general, all of these minor losses are due to turbulent action within the fluid. So you'll get some turbulent eddies that form in these stagnation zones. And then also as the streamlines move into the smaller pipe, they will start to separate from the wall in this zone here. And as they separate, they will also form some turbulent eddies that cause energy losses. So let me just label, this is point 1. This is point 2. At point 1, you have some velocity u1. And at point 2, you have some velocity u2. We can take a look at the energy grade line as we move through this contraction. So in general, it'll look something like this. So you'll get a pretty steady energy grade line until you encounter this zone here. You'll get the energy starts to decrease. And then as you move into the smaller pipe, the energy decreases more rapidly until it eventually settles out. So this is the EGL. We can also draw the HGL. So here's our hydraulic grade line, which tracks the piezometric head. As we encounter this transition, the HGL will also decrease, except it'll decrease more than the EGL. And you'll get something that looks like this. So why is the distance between the EGL and HGL greater in the smaller pipe than in the larger pipe? Yes.
Faster velocity.
Very good. So we have faster velocity in the smaller pipe. What is the difference, the mathematical difference between these two lines, the EGL and the HGL? What do you need to add to the HGL to get the EGL? Very good. So the distance between these two lines is u squared over 2g. So here we have u2 squared over ug, sorry, 2g. Here we have u1 squared over 2g. Because u2 is going to be faster than u1 by continuity, the distance between the EGL and the HGL increases as you move into the smaller pipe. So the general form for our contraction losses is as follows. We have h little lc will be equal to some coefficient kc times u2 squared over 2g. So note that here we're using the velocity in the faster pipe. This is a convention, so this equation is semi-empirical. Just by convention, we use u2 instead of some combination of u2 and u1 for computing the minor losses. This coefficient kc depends on a couple of quantities. So kc, our contraction loss coefficient, will in general depend on the velocity of flow in the smaller pipe, as well as the ratio of the diameters. So ratio of d1 divided by d2. So let me go ahead and just open up a table to show you. I'll let you finish writing this down. Are there any questions on contraction losses, sudden contraction losses? Okay, so this is something you encountered in fluid mechanics. We can go to our tables just to get a sense of what these contraction loss coefficients will look like. So let's go here, table 3.5. So these are loss coefficients due to sudden contractions. And you can see they depend on both the velocity in the smaller pipe, as well as the ratio of pipe diameters, so d2 divided by d1. So you have to have access to both pieces of information, and they generally range from about 0.5 to about 0.03, 0.01-ish. So there's quite a range in contraction coefficients. All right, so one way that we can reduce these losses, generally, they may be seen as undesirable. So one way we can reduce sudden contraction losses is by putting in a gradual transition. And this will reduce but not eliminate the head losses. So in addition to sudden contractions, we also have gradual contractions. So here we might have a larger pipe gradually transitioning into a smaller pipe using a device called a confuser. So we might have a velocity at the upstream end, u1, some cross-sectional area at the upstream end, a1, cross-sectional area at the downstream end, a2, and a velocity at the downstream end, u2. So our general equation for the minor losses in this gradual contraction will be of the form h little l, and then I'll call it c prime. And this will be equal to some coefficient kc prime times, again, u2 squared over 2g, where the coefficient kc prime depends on the same quantities as earlier. So this depends on the same quantities as used for kc. So velocity depends on the ratio of diameters. But it also depends on something else. Can anyone guess what else it will depend on for this case? I heard someone say slope. So basically the angle of the contraction. So a more gradual contraction will have less losses, and that's defined by the angle. So we have some angle alpha associated with this transition. Basically, you can think of this as the angle, like if you take this triangle and you extend it all the way, it would be this angle here. So this here is our angle alpha. Questions on gradual contractions? Yes.
So those are the same.
Yes, that alpha there and that yellow alpha there are the same. I'm just trying to make it clear what that angle is. So just to give you a sense of what these contraction losses look like, we can go look at a table of gradual contractions. So this is a table of gradual contraction coefficients depending on again, the angle of the contraction as well as the ratio of the areas in this case, which is proportional to the ratio of diameters. So you might see the contraction losses expressed like this, where it's a function of the ratio of the areas, cross-sectional areas of the two pipes. And again, most of these tabulations are empirical, so they may differ between different sources. The final type of contraction loss I want to talk about is basically the extreme case of a sudden contraction. So let's imagine that you take this area here for the larger pipe and you just make it extremely large. Then you have what's called an entrance loss, which is essentially the losses associated with moving from a reservoir to a pipe. So if you basically take the extreme case of the sudden contraction, you get the entrance loss, entrance here meaning the entrance into a pipe from a reservoir, which will take the form, again, H little l e is equal to K E times U squared over 2G. And let me just draw a diagram to make it clear what I mean here by U. So let's say we have a reservoir that transitions into a pipe. U here refers to the velocity in the pipe. And on the upstream end, we have a reservoir with some water level. This is a wall right here. And your KE coefficient, I'm not going to write out all the different cases here, but KE depends on the shape of the transition. So generally it's in the range of, about like, it can range all the way from 0.04-ish to 1, depending on the shape. So it's quite a range. For a sharp-edged contraction or a sharp-edged entrance loss like this, it'll be about 0.5. So let me go ahead and show you the table of different entrance losses. So again, it will depend on the shape of that transition. In most cases, we're going to be looking at just sharp edge transitions like this. So a KE coefficient of about 0.5. For other cases, like a rounded entrance, it can be as low as 0.04. For a re-entrant pipe, it can be all the way up to 1. So quite a bit of variation in that loss coefficient. Okay, any questions on entrance losses? I know I'm moving a bit fast here, but I definitely want to get to our example today. Questions on entrance losses? All right, so we covered contractions. Next, let's just talk about expansions. So first, we're going to talk about sudden expansions. So this is essentially the opposite case. We have a small pipe going into a larger pipe. This might occur, for instance, if you have some sort of pump that discharges into a small pipe that needs to go into a water main. So it's another pretty common case. So we'll have some velocity U1 on the upstream end, some velocity U2, the downstream end. And as I mentioned, we're going to have streamlines that are transitioning from the smaller pipe into the larger pipe. As they enter this larger pipe, they diverge. And again, in these pockets here, you'll get some turbulent eddies that form. And those are the major source of these losses. So we can again draw the EGL and the HGL. The EGL will look something like this. You'll have a higher EGL on the upstream end. That EGL decreases as you go through this turbulent region, and it kind of steadies out on the downstream end. The HGL will look something like this. So you'll have an HGL that starts out lower. As it moves into this transition, it's going to dip down, and then it's going to move back up. So in this case here, it actually ends up higher than it was before. So this is our EGL. This is our HGL. And again, the difference between the EGL and the HGL is U1 squared over 2G on the upstream end, U2 squared over 2G on the downstream end. So the equation for the head losses due to sudden expansions can actually be derived theoretically. It's one of the nice cases where we can actually derive it theoretically and we don't need an empirical formula. And it turns out to be really simple. It's equal to U1 minus U2 all squared divided by 2G. So basically this can be, this expression for the minor losses can be derived from applying the momentum equation. It's in the course packet. I won't go through it here just because it'll take too much time, but you can derive this formula for the head losses associated with a sudden expansion explicitly. Questions on expansions or anything on this slide?
So capital E is for this one, and then lowercase e is for the big.
Yes, so in my notation here, capital E is for sudden expansion. Little e is for entrance loss. All right, so just like with contractions, we can reduce these head losses by applying a gradual transition. So we might have gradual expansions, kind of the same idea as with gradual contractions. We'll have a smaller pipe transitioning into a larger pipe through something called a diffuser. Bless you. Bless you. And again, we'll have some velocity U1 at the upstream end, some velocity U2 at the downstream end, and there'll be some angle associated with this diffuser that is going to determine our head loss coefficient. Now, this equation here, the book actually has this equation wrong, so pay attention. The minor losses associated with a gradual expansion are given by, I'll write it as H little l capital E prime. This is equal to a a gradual contraction coefficient Ke prime times quantity U1 minus U2 squared divided by 2G. So the book actually has this equation wrong. Use this equation here. Oh, also the book has the equation for the Colebrook-White equation wrong. So just use my notes instead. So again, the expansion loss coefficient in this case depends on that angle. So we can take a look at some examples here. So again, the range is pretty large. It can range from 0.08 on the low end all the way to getting close to 1 at the high end. And you can imagine as that angle approaches 90 degrees, it becomes 1. Any questions on gradual expansions? We've just got a couple more to cover, and then we're going to get to an example. So just like the entrance losses were kind of the extreme case for contractions, we also have the extreme case for expansions, where a pipe empties into a reservoir. We'll call those exit losses. Another pretty common case. So let's say we have a wall right here and a pipe. I'm going to move this down a little bit. So we have a pipe coming into a reservoir. We have some velocity u in the pipe. And as the water enters the reservoir, again, you get this divergence in the streamlines and some turbulence forming at the wall. So our expression for exit losses is really simple. It's basically the extreme case of the sudden expansion. So what happens here if U2 goes all the way to 0? We just end up with the head loss is equal to U1 squared over 2G. So the case for exit losses is just going to be H little l. I'll call it D for discharge. Unfortunately, most of these words start with E. So H little LD for our exit loss will be equal to U squared over 2G. So we can also draw the EGL and the HGL. So the HGL will actually just be kind of a straight line that intersects with the reservoir surface. Okay, so it just transitions gradually into that water surface. The EGL will be a parallel line that's above the HGL until it hits this turbulent region here. And then the EGL very quickly goes down and becomes equal to the water surface. So basically all of the velocity head in the pipe is lost. The difference in energy between the pipe flow and the reservoir is just equal to U squared over 2G. Okay, any questions on exit losses? So we have a couple miscellaneous cases to cover. I'll just go through these quickly because again, they're all just going to be some equation of the form K U squared over 2G. So as mentioned at the beginning of class, we have head losses in bends. something that looks like this. You'll have some diameter associated with the pipe. And then you'll have some radius associated with this bend. So if you imagine a circle basically subtending this bend, there is a radius associated with that circle. You will have streamlines within the bend. And as I mentioned at the beginning, the streamlines at the inner wall of the bend will tend to separate from the wall as it goes through that bend, and they'll cause turbulent eddies along this edge. So that's where you will get your losses. We have some velocity coming through this bend of u. And so our head losses are given by the expression h little lb for bend is equal to kb times u squared over 2g. So no big surprise there. The bend coefficient depends on, in general, the ratio of the radius of the bend to the diameter of the pipe. So I'll show a table shortly. But again, it's kind of the same story here. So if we go to our tables, there should be a table here showing the different bend loss coefficients. So again, it depends on the ratio of the radius of the turn to the diameter of the pipe, and it can range depending on that ratio, kind of in an unpredictable way. So you'll notice that it actually decreases at first and then starts increasing again. So generally, this is something you'll have to look up in a table. And the final type of loss I want to talk about is head losses in valves. Again, this is generally empirically determined, and it'll take the form h little lv is equal to kv, our valve loss coefficient, times u squared over 2g, where kv just depends on the type of valve. So kv, as in Victor, depends on the type of valve. kb, as in Bravo, depends on the ratio of the turn radius to the diameter of the pipe. And just like with valves, other obstructions in the pipe often have tabulated loss coefficients. So for instance, flow meters will also have loss coefficients associated with them because they interfere with the path of flow. Things like turbines, obviously, anything that interferes with the flow of water will have some minor loss coefficient. So we can take a look at just what those valve loss coefficients might look like. And they have a pretty big range. So it depends on the type of valve. It can range from, something pretty small for gate valves on the order of 0.15 to pretty large. So for check valves, for certain types of valves, they can go all the way up to 70. By the way, who knows what a check valve is? What does a check valve do? I feel like there needs to be a whole plumbing module in this class because it's something I had to pick up on my own. So from this diagram, can you guess what a check valve does? Yes. Yeah, so it prevents flow from going the wrong way. So you might want to have this on a line coming out of a pump, for instance, if you don't want the water flowing backwards. There are also other types of valves like pressure release valves, pressure regulating valves. So it's a pretty interesting subject. Maybe I'll incorporate more of that into this class at some point. All right, are there any questions on the different types of minor losses? At this point, I'm going to move on to an example that will take the rest of class. Are there any conceptual questions about the types of minor losses that I surveyed today? No. No? No. Okay. So on Canvas, under Files, I've uploaded a starter sheet for you, so go ahead and download that now. You'll still need your, pen and paper out because I'm going to be going through the actual problem. But just note that under lecture notes, lecture 7, there will be a file called minor losses example starter. So go ahead and download that when you get a chance. I'm going to start writing down the problem statement now, so have your notebook ready. So this is an example that's going to synthesize basically everything that we've done in this class so far. So applying the energy equation, applying frictional loss models, and applying minor loss models. This is a good example to look at as you prepare for the first exam. So I'll write down the problem statement. We have a cast iron pipe that is transporting water. So I'll say cast iron pipe transports water from a reservoir into the air through I'll just say 2-section pipeline that terminates in a rotary valve located 100 meters below the water surface in the reservoir. So if the water is 10 degrees Celsius, compute the flow rate in the pipeline. So I'll have to draw the rest of this problem for you. So we have a reservoir. There's some water level in the reservoir. And it discharges into a 2-section pipeline. So this is going to be a pipeline with 2 different diameters. So the first section will have a larger diameter that transitions into a second section with a smaller diameter. And that smaller diameter pipe terminates in a rotary valve. So I'll draw that like this, a little diamond, hourglass shape. And the water discharges from this rotary valve into the atmosphere. Yes. So it discharges into the atmosphere. So i.e. not into water, not into another reservoir. So the first pipe will have a length delta x1 of 1,000 meters and a diameter of 40 centimeters. The second pipe will have a length delta x2 of 1,200 meters and a diameter, half the diameter of the first pipe, so that'll be 20 centimeters. And importantly, the valve, we're going to assume that the cross-sectional area of the valve is the same as that of pipe 2. So I'll say, the, rotary valve. This has the same cross-sectional area as pipe 2. All right, so our job is, we know the distance between the discharging valve and the water surface. So this distance here, this is 100 meters. And our job is to determine the discharge into the atmosphere. So what do you think a good place to start with this problem might be? Yes.
I have a question. So the height goes down where the diameter.
Are you talking about this yellow line here? It goes down to the center line of this valve right here. So let me just draw. Okay, almost got it there. So what would be a good place to start with this problem? Energy equation. So that's usually the answer for this class. So let's apply an energy balance. I'm going to put 3 different points. Actually, I'll put 4 different points here. So we have point 0. So that is at the surface of the reservoir. We have a point 1, which is right at the entrance of the pipe. A point 2, which is right at the transition between the 2 pipes. And then a point 3, which is at the point where the water discharges into the atmosphere. So those are the 4 different locations that we can use for the energy equation. And first we have to choose what 2 points to apply our energy equation across. So generally you'll want to look for the points where you have the most information. What 2 points do you think we have the most information? 0 and 3, right? So we have some extra information about 0 and 3 because they are basically boundary conditions for the system. So let's apply an energy balance between 0 and 3. So from our energy equation, we have PO over gamma. So that's pressure at the water surface over gamma, the specific weight, plus ZO, the elevation of the water surface above some datum, plus UO squared over 2G. So that's the velocity at the surface of the reservoir. This is equal to P3 over gamma. That's the pressure at the outlet divided by the specific weight, plus Z3, the elevation of the outlet above some datum, plus U3 squared over 2G, the velocity of the flow exiting the rotary valve. And then to that, we need to add all of the head losses. So I'm just going to group these together as H big L. So that includes all the head losses, both from the minor losses as well as from the frictional losses. So looking at this energy balance here, which terms can we simplify here? So what are some terms that we can just get rid of outright? Which terms here are equal to 0? Yes. So P0 and P3 are both equal to 0 because at the surface of the reservoir, the pressure is equal to gauge pressure at 0. P3 is also equal to 0 because it's open to the atmosphere. Any other terms we can get rid of? Yes.
U0 velocity.
Yes, so the velocity at the surface of the reservoir, we can also assume is negligible. And we don't have Z0 and Z3 explicitly, but we do have the difference between Z0 and Z3. What is that equal to? 100 meters. So we have the Z0 minus Z3. I'll call this delta Z, and this is equal to 100 meters. So I'm just going to go back and write that on this diagram here. So this is delta Z, and this is equal to ZO minus Z3. So we can rewrite this first equation as delta Z is equal to U3 squared divided by 2G plus the head losses. Okay, there's one more simplification we can make so that we don't have to keep track of multiple different velocity variables. So we have in pipe 1, we have some velocity U1. In the reservoir, we have U0 is equal to 0. In the smaller pipe, we have some velocity U2. What is the velocity at the valve at 0.3? What is it equal to? It's equal to U2. So remember that I said the rotary valve has the same cross-sectional area as pipe 2. That means the velocity at the rotary valve has to be equal to the velocity of pipe 2 by continuity. So just note that A2 is equal to A3. Therefore, U2 is equal to U3. So we have that U2 is equal to U3, and thus we can re-express our energy balance as delta Z is equal to U2 squared divided by 2G plus all of the losses. So now we don't have to keep track of U3 and U2 separately. Okay, so let's break down the head losses. There are two main types in this problem. Our total head losses are equal to the sum of our major losses. So I'll write this as H major plus H minor for the minor losses. So we need to account for both of these losses now. Let's take a look at the major losses first. So how can we determine our major losses here? What equation do you think we should use here? Darcy-Weisbach. So because the problem statement gives the temperature, you probably want to use Darcy-Weisbach because Darcy-Weisbach is the only equation that accounts for the temperature and the viscosity. So for this class in general, unless otherwise stated, use Darcy-Weisbach to compute frictional losses. So we have Darcy-Weisbach, and we have two different pipe sections. So we have to apply Darcy-Weisbach to each pipe section because the velocity is going to be different in pipe 1 than it is in pipe 2. So we can write the major losses as the sum of the losses in pipe 1 plus the losses in pipe 2. So for pipe 1, we have friction factor for pipe 1 times delta x1 divided by d1 times u1 squared over 2g. For pipe 2, we add to that F2 times delta x2 divided by d2 times u2 squared over 2g. So we have to add together the frictional losses from the first pipe to the frictional losses in the second pipe, and the two pipes have different lengths and diameters and velocities. Okay, so we have our expression for the major losses. I'm just going to leave it at that for now. We also have our minor losses. So let's go ahead and first we just have to list out what the minor losses are. So let's go back and take a look at our diagram and see if we can identify what all of our minor losses are for this problem. Okay, so what are the types of minor losses that you see here? Yes?
First one is like the big contraction, like reservoir into.
Oh, this one. So do you remember what this is called? Sorry? There's a specific name. Entrance. So with all of these names, it refers to the pipe as being the object of interest. So it's the entrance into the pipe. I know it's a bit confusing, but this would be our entrance loss. So we have our entrance loss from the reservoir to pipe 1. I think someone else mentioned the sudden contraction. So at point 2, we have a contraction. This is sudden. And there's one more. The valve loss. So the rotary valve will have a loss associated with it. So I'll just call this a valve loss. All right. So our minor losses, I'll write this as H minor is equal to the entrance losses. I'll call this H entrance just to be explicit, plus H contraction plus H valve. So let's go ahead and try to populate each one of these expressions for the minor losses. So first we have the entrance loss. This is going to be of the form KE or K little e times U squared divided by 2G. So what U is this here? Let's look back at the diagram. U1, very good. This is U, let me draw this a bit bigger here. So this is U1 squared over 2G. Okay, for the contraction, we have KC times U squared over 2G. Which U is this? U2. And then we have H valve. This is going to be of the form KV times U squared over 2G. And again, this will be U2, which is equal to U3. So let's go ahead and try to populate each of these coefficients. I'm going to go back to pages and let's go down to reference. Okay, so first we need the entrance loss. So that's in this table here. And we have a couple different options to choose from. So you might think that it's this one here. Turns out that the angle is just very small. So I'm going to go ahead and use this first option here. KE is equal to 0.5 for a sharp edged entrance into the pipe. If someone wants to check what the angle is, you can go ahead and calculate that and then tell me, but I'm pretty sure the angle is going to be basically negligible here. So KE is equal to about 0.5. Then we have our sudden contraction. So that has its own table here. And okay, now we have a decision to make. So it depends on both the velocity in the smaller pipe as well as the ratio of pipe diameters. So what's the problem here? Yeah, we don't know the velocity yet, so we don't know the discharge, so we can't compute the velocity. So we're gonna have to make an educated guess. We do know what the ratio of smaller to larger pipe diameters is. So the larger pipe diameter is 40 centimeters, the smaller pipe diameter is 20 centimeters. So our ratio is 0.5. So our coefficient is going to be somewhere in this column. I'm going to go ahead and just pick 0.33. So velocity of 6 meters per second. That actually seems pretty high, but I'm just going to go ahead and pick that entry, and we're going to adjust our answer after we solve for the discharge. So I'm going to go ahead and pick 0.33 as our first guess. And then finally, we have our valve loss coefficient. So we have to look that up in our table as well. So this is a rotary valve. And we can see that for rotary valves, the valve loss coefficient is going to be 10. So this is going to be the largest source of the minor losses for our system. Are there any questions on how I specified those minor losses? Yes.
The tables for the contraction one, do we interpolate that or do we just go to the?
Ideally, you would interpolate, but it's going to turn out it doesn't really have a very large effect on the answer for the range that we're looking at. So if you looked at that column, the values range from about like 0.3 to 0.38. And it's going to be a relatively small contribution to the head loss, but ideally you would interpolate, yes. All right, so what we're going to do now is we're going to go back to our energy equation and we're going to plug in all of those head losses for in this HL term here. So let's go back and substitute in our energy losses. So from our energy equation, we have the delta Z is equal to U2 squared divided by 2G plus the head losses. And these head losses are going to be the sum of the major and minor losses. So for the major losses, we have F1 times delta X1 divided by D1 times U1 squared over 2G plus F2 times delta X2 divided by D2 times U2 squared divided by 2G. So those are our major losses. To that, we need to add our minor losses. So that's going to be plus KE for the entrance loss times U1 squared over 2G plus KC times U2 squared over 2G plus KV times U2 squared over 2G. So I'm going to go ahead and just make a quick rearrangement here just to simplify things. So I'm going to take this delta Z and I'm going to subtract it from both sides. So we'll end up with 0 is equal to negative delta Z plus this entire expression here. So you'll notice that all of the terms here in these losses depend on either U1 squared over 2G or U2 squared over 2G. So we can simplify just by grouping together our terms based on whether they're multiplied by U1 squared over 2G or U2 squared over 2G. So I'm going to do that. We have that 0 is equal to negative delta Z plus, okay, so first I'm going to group together all the terms that depend on U1 squared over 2G. So that's going to be this first frictional loss here and our entrance loss. So we'll have F1 times delta X1 divided by D1 plus KE all times U1 squared over 2G. Our next term is going to depend on our terms that are multiplied by U2 squared over 2G. So that includes the velocity head at the valve, this term here, the frictional loss in pipe 2, the contraction loss, and the valve loss. So we're going to end up with 1 for this first velocity head term here, plus F2 times delta X2 divided by D2, plus KC, plus KV, all times U2 squared divided by 2G. And now note here that U1 is equal to Q divided by A1. And U2 is equal to Q divided by A2. So we can use this expression here to solve for the discharge in the pipe. Yes,
Is discharge the same for the whole?
yes. So by continuity, the flow going into the pipe has to equal the flow going out, or else there will be some accumulation in the pipe, which can't happen because it's pressurized and completely full. So I know that that might seem unintuitive, but you can be sure of the fact that for any problem involving pipe flow, the flow coming in has to equal the flow coming out. All right, so we got about 10 minutes left. What I want to do is I want to solve this problem. So basically this equation here, this is going to be our objective function. And our decision variable is going to be the discharge Q. So we're basically going to just keep trying different values of Q until this right-hand side of the equation evaluates to 0, meaning that our system of equations is satisfied. So let's go ahead and do that. So I gave you a Excel sheet at the beginning of class. Let's go ahead and open up that Excel sheet. And I think I need to download it myself here. All right, so we got lecture notes, lecture 7. Let's go ahead and download it. All right. So let's go ahead and fill in these parameter values first. So I've set up these parameter values for you for convenience. So for the length of pipe 1, we have 1,000 meters. For the diameter of pipe 1, we have 40 centimeters, which is 0.4 meters. For the roughness height, has anyone looked this up yet for cast iron? I believe it's 0.26 divided by 1,000. So 0.26 millimeters, yes. So there are power strips distributed around the room. If you can move to one of those, you should be able to use the outlet. There's also an outlet right up here. Yeah, if you want to use that one. All right, so we have the length, the diameter, the roughness height of pipe 1. Next, we need the length of pipe 2. So this is 1,200. D2 is 20 centimeters, so that's 0.2. Roughness height is 0.26 millimeters divided by 1,000 equals 0.00026 meters. For our entrance loss coefficient, what was this again? 0.5, very good. For our initial guess for the contraction coefficient, we had 0.33. For the valve loss coefficient, we had 10, very good. Gravity is 9.81 because we're in SI units. The viscosity, I didn't look this up, but I think it's 1.307 times 10 to the negative third. So if someone can check that for me for 10 degrees Celsius after I set up the spreadsheet, that would be helpful, but I'm pretty sure that's the correct one. Delta Z is 100 meters. Pi is 3.1415. And rho, I believe, should be about 999 kilograms per cubic meter. Okay, so next we have some quantities that we can compute to make the objective function easier to express. So the area of pipe one, cross-sectional area, this is going to be pi times the diameter of pipe one squared divided by 4. So let me go ahead and paste this formula out to the side just so you can double check. Okay, the velocity of the flow in pipe one. So first we need the discharge. So what I'm going to do is I'm going to go up to column C. Our decision variable is the discharge, and this is in cubic meters per second. I'm going to start with an initial guess of 0.5. So we can compute the velocity by dividing this discharge by the cross-sectional area. So for U1, this is going to be C2 divided by B17. And I'll paste this formula out to the side. Okay, Reynolds number in pipe one. How much time do we have here? Oh, okay, we gotta hurry. Okay, so we need diameter in pipe one times the velocity in pipe one. I'm actually going to use the absolute value of the velocity in pipe one just to prevent the Reynolds number from becoming negative, which it shouldn't do. Okay, so diameter times velocity times the density divided by the dynamic viscosity. Paste that formula out to the side. I think I just didn't copy it. 1 second. Okay, E1 over D1. So this is just E1 divided by D1. So that's cell B4 divided by B3. And the friction factor, okay, so for this, I'm going to use Swami Jane because we don't want to deal with 2 different Colbrook-White equations to solve. So this is going to be 0.25 divided by log 10 of E over D divided by 3.74. I'm doing it from memory here. Oh wait, no, okay, I found it. Plus 5.74 divided by the Reynolds number to the 0.9 power, and then we need to square the whole denominator. So double check that for me because it's kind of long. Okay, so for A2, U2, Reynolds number 2, so all these are basically the same. So A2 is going to be diameter 2 squared times pi divided by 4. U2 is going to be Q divided by A2. Reynolds number in pipe 2 is going to be diameter 2 times velocity 2, or absolute value of velocity 2, times the density divided by the viscosity. E2 over D2 is just E2 over D2. So this will be cell B7 divided by cell B6. And for Swami Jane, for the friction factor, we'll use 0.25 divided by log 10 of E2 over D2 divided by 3.7 plus 5.74 divided by the Reynolds number to the 0.9 power, all raised to the second power. I heard someone run the solver, I think. So these are those expressions here. I need to move to the objective function. So if you don't have all of these, try to figure them out based on the equations that we have, and I'll come back to them afterwards. So we need to specify our objective function. Our objective function is given by that energy balance from before. So our objective function is going to be this equation here. So for our objective function, we have negative delta Z. So that's going to be negative cell B13 plus our expression for the first set of losses. So that's going to be F1 times delta X1 divided by D1 plus KE all times U1 squared over 2G. So that is U1 squared divided by 2 divided by G. So I'm not finished yet, but I'm going to paste these out to the side. So term 1 is the negative delta Z, and that's just negative B13. For term 2, we have this expression here. And for term 3, we are going to add the next set of losses. So that's going to be plus quantity 1 plus F2 times delta X2 divided by D2 plus KC, so that's cell B9, plus KV, all times U2 squared over 2G. So that's going to be U2 squared divided by 2 divided by G. So I'm running out of time here. Let me go ahead and see if we specified our problem correctly. So I'll return to this at the beginning of class next time, but let's just check here and see if we got our problem set up correctly. So I'm going to go to data solver. We're going to set our objective to cell D2. We're going to set it to a value of 0 by changing cell C2. Let's go ahead and run. And I happen to know that this is the correct answer. So our discharge turns out to be 0.116-ish. I'll return to this at the beginning of class on Tuesday. But have a nice weekend, and please come to office hours if you have questions about homework too. Yes. Not the one due tomorrow.
Yeah,
Okay. I'll be in my office. You want to do it? Okay, let me just exit my recording. Okay.